In this example, we're going to look at a ramp voltage of 10 volts per second put across an inductor and resistor in series. This is quite an awkward one and requires us to use the method of partial fractions again, but with quadratic factors, which adds another factor, as we'll see. The method is outlined in the maths textbook in the chapter on partial fractions, if you care to have a look, section 7.4. Anyway, let's work through this example. So the first step is, as before, the current. We're going to analyze the current, which is given by Ohm's law, and we need to work out what that is by using Laplace transforms. So the first step, find the Laplace transform for the voltage and for the total impedance. So again, as I go through this, you could pause at various points and see if you can carry on from that particular point. So ES is going to equal 10 over S squared, and ZS is going to equal 6 plus 4S. 6 plus 4S. Putting these into Ohm's law, 10 over S squared over 6 plus 4S. Again, bringing the S squared down, as we did before, we get I over S. So IS equals 10 over S squared into 6 plus 4S. And this is where we need to consider the fact that in this part of it, we've got a quadratic factor. And so using the method of partial fractions, we have to split this and have a 3 terms to take this into account. And so I'll start this off and, on the next slide. Okay, so here we have to say that the 10 over S squared into 6 plus 4S equals a factor involving S plus another factor involving S squared plus a third factor for the 6 plus 4S term. And so this is the extra term that needs to be added because of the S squared, the quadratic factor. But the process is the same after that, it just gets a little bit more involved. Again, we have to effectively cross multiply. I have to multiply to get the same denominator, each term, or to get the denominator S squared into 6 plus 4S in the bottom here, I have to multiply the top by S times 6 plus 4S. Similarly for the second term, what have I got to multiply the top by to get the factor S squared into 6 plus 4S on the bottom? And what do I have to multiply the last term by to get S squared into 6 plus 4S on the bottom? Well, this one I need to multiply by 6 plus 4S, and this one I need to multiply by S squared. Now I can equate numerators because the denominators on the left and the right hand side are the same. So equating numerators, I can write that 10 equals A S 6 plus 4S plus B 6 plus 4S plus C S squared. Now multiplying out the brackets, 6AS plus 4AS squared plus 6B plus 4BS plus CS squared. Now we're going to equate coefficients on the left and right hand side. What are the coefficients of s squared on the left? 0. So collect together all the s squareds on the right and make them the same. What's the coefficient of s on the left hand side? 0. So collect together all the terms involving s on the right hand side and make that equal to 0. And then finally, the constants must equal 10. So write down 3 equations. You should get that. If we collect together terms involving s squared, 4a plus c s squared, and then collecting together terms involving s, 6a plus 4b s, and then finally plus 6b. So now we can equate coefficients and write down 3 equations. 1, 6b must equal 10 because the constants left and right must be the same. 4a plus c must equal 0 because s squared terms left and right must be the same. And finally 6a plus 4b equals 0. So I've got 3 equations and 3 unknowns, a, b and c. So simultaneously I should be able to solve those. See if you can do that. So from the first equation, numbering these equations 1, 2 and 3. So from equation number 1, b equals 10 over 6, which is 5 over 3. Putting this into equation 2, I could work out what c was, and then into equation 3, I could work out what a was. No, putting equation 3 to find out what a is, and then knowing a, we can put that into equation 2 to find c. So carry on and solve those. So we should get these values for a, b and c. b equals 5 over 3, or 1.67. a equals minus 10 over 9, or minus 1.11. And c equals 40 over 9, which is 4.44. So now we put these back into the original equation. And writing that down, we get is equals minus 1.11 over s plus 1.67 over s squared plus 4.44 over 6 plus 4s. And you can see that these are pretty well in the form to transform them back using the Laplace transforms. The only thing is, again, we have to remember that the table only involves s on its own, so we need to divide all terms top and bottom in this last fraction by 4 to get this on its own. And then we can do the tables, use the table to transform back. So see if you can finish that little bit off and arrive at the solution. IT equals minus 1.11 plus 1.67t plus 1.11 over 1.5 plus s. And so, what am I saying? Transform back, this will give us plus 1.11 e to the minus 1.5 t. We can write this by rewriting this maybe a bit more helpfully, 1.67t and then minus brackets minus 1.11 rather, and then writing this term here, 1 minus e to the minus 1.5t. So again, there's some sort of exponential growth term involved with this. To a limit, but we also have a factor of 1.67t in there. Putting this into autograph, we can see what the thing's going to look like. So again, typing it in, y equals 1.67 x minus 1.11 brackets 1 minus e to the power minus 1.5 x. Okay. And we see, again, we're only interested in what happens after t equals 0. And we can see that the transient period is right at the beginning, around here somewhere, so you can zoom in on that part of it, and it looks as though it settles down to a steady ramping voltage, which is what we would expect if you think about the original circuit. After a period of time, the inductance is going to have a steady effect as the voltage builds, and so we'll end up with a steady building voltage, again over the time, assuming that the voltage continues to rise at the set rate, which won't happen in practice. So we could zoom in on the transient period and note that there's some sort of exponential term involved with the first part of the circuit before it settles down to a steady state. I've plotted the two curves. You can see them here. That's the one we're just looking at on autograph in the notes. And below, I zoomed in on the transient period, and it looks as though it settles down to a steady voltage at around about this point. And so it's about 1.2 seconds maybe. So that would be the transient period in this circuit. You could have a go at this one below, and I'll put the solution underneath. This is the function that you should get for the current. The current equals 0.2t minus 0.08, 1 minus e to the minus 2.5t.